So, question number 8. Figure 8.1 shows a ripple tank and a crust of the water that is produced in it. So, this whole setup is called as ripple tank. Ripple tank is a device, it's a tool that we use to produce water waves. And once we produce the water waves in it, in the laboratory, once we produce the water waves, we can study some of the properties, some of the uh, processes like reflection, refraction, and diffraction as well. And diffraction is a topic which has been recently added in the syllabus for O level physics. Anyway, let's move on to the first question. The frequency of the water waves is 2.0 hertz and its amplitude is 3 millimeters. So the frequency is 2 hertz and its amplitude is 3.0 millimeters. Calculate the number of crusts produced in 1.5 seconds. Alright, so we need to find the number of crusts that would be produced in 1.5 seconds. So the thing is, the frequency of the water wave is 2 hertz. Now what does that mean? That means it would be exactly 2 waves, or you can say 2 crusts per second. This is how we define frequency. So 2 hertz would mean 2 waves or 2 crusts per second. But in 1 second, we have 2 waves. I can write time over here. So in 1 second, we have 2 waves. Then how many waves do we have in 1.5 seconds? Can be solved by different ways, or you can use a method of cross multiplication as well. So in 1 second, we have 2 waves. How do we know that? Because the frequency of the wave is 2 hertz. That means there would be exactly 2 waves, or exactly 2 number of crusts. There would be 2 crusts in 1 second. And if you need to find the number of crusts in 1.5 seconds, you can do it by method of cross multiplication, or you can simply multiply that. That's the same thing. So 1.5 times 2, that would be your value of x, which in this case represents the number of crusts, and that would be 3. So 3 crusts would be produced in 1.5 seconds. Don't write anything, no unit with 3, because it just represents a number. So it has to be without any unit. Moving on to the next one. The height of the wave is measured from the level of the undisturbed surface of the water. The height of the wave at one point is 0 at time 0. On figure 8.2, draw a graph to show how the height of the wave at this point varies with time. So in other words, you have to draw displacement time graph. So displacement over here, which would be representing your amplitude as well, displacement on the y-axis and time on the x-axis. In waves, general wave properties, in the water waves we have 2 important graphs. One is displacement time graph and the other one was displacement distance graph. If instead of time either represent distance in meters or centimeters or millimeter, whatever it is, then that would be called a displacement distance graph from which we can directly find the wavelength. But from the displacement time graph, we cannot directly find the wavelength. Rather, we can find the time period and we can also find the frequency. And if the speed is given, then indirectly from mathematics, we can find the wavelength. So now we have to draw the graph first. All right. So once again, you have to first take a notice about the amplitude. So amplitude was 3 millimeters. Here the amplitude is 3 millimeters and height on the graph is also in millimeters, so we don't need to consider the unit conversion or anything for the y-axis. On the x-axis we have to represent time, which is in second. So you need to be careful with two things. I must be writing here. The first thing is you have to be careful about the peak. What should be the maximum value of your wave? What should be the amplitude? So your peak of the wave should correspond to the amplitude of the wave. And the second thing that you need to consider is frequency or time period. Frequency or time period. You can complete this from the perspective of time period or from the perspective of frequency at your convenience. Now what I'm going to do is, since I know that the frequency of the wave is 2 Hertz, frequency of the wave is 2 Hertz. Alright, that was given in the question. So frequency is 2 Hertz, 2.0 Hz, Hertz. What does that mean? Well, it means in 1 second, you must be having 2 complete waves. And before we start anything, we should be marking the central line as well. So your wave should be equally distributed above and below that line. Alright, so moving on to the next part. The frequency of the wave is increased. Describe how the apparatus shown in figure 8.1 is adjusted so that the frequency of the wave is increased. You have to increase the frequency. What are the adjustments that you make in the apparatus so that there are more number of waves produced per second? Now let's take a look at the figure that they are referring to. It is figure 8.1. So the waves, you see, the waves here are being produced with the help of this wooden bar, which is attached to a rubber band. And then you have a rod, then you have a cane here, of which we might be moving up and down in the water to produce the water waves. So how do we change the frequency? How do we increase the frequency? Well, we have to make the same wooden block move faster. So the bar that the wooden block is attached to with the help of the rubber band, we move the bar, we move the cane up and down faster, so that more number of waves would be produced. So I can write here, move the bar up and down faster. All right, if you do so, there would be more number of waves produced, and the more the number of waves, the more the frequency. Then we have the next one, state what happens to the speed and the wavelength of the wave as the frequency increases. So as the frequency increases, it means the wave is now compressed. There are more number of waves, quickly, more number of waves per second. Wave is traveling faster, it's kind of compressed. So if the wave is compressed, the wavefronts are close to one another, then the wavelength would be decreased. All right, so in simple words, frequency and wavelength, they will go against each other. We study one thing, that red color has the highest wavelength. It has the highest wavelength, and it has, at the same time, it has the lowest frequency among all the colors from the visible light. So these two things go against each other. Now, the thing about the speed is, the speed of the wave would remain same. All right, so speed is basically speed of a wave depend on these two things, frequency times wavelength. And if you have increased one thing, you increase the frequency, but in response to the increase of frequency, there is a decrease in wavelength, and the product would once again be same. For example, your frequency previously was 2 2 hertz and the wavelength was 3 meters. If you increase the frequency to 3, then the wavelength would be reduced, so let's say to 2. What is the product of frequency and wavelength here? 6. That is your speed. What is the product of frequency and wavelength here? That is still 6. So frequency increases, then the wavelength also increases proportionally, and hence the speed remains same. Moving on to the next one, part C. The apparatus shown in the figure 8.1 can be used to demonstrate refraction. So where is the yeah, the same one. Like I said, this ripple tank can be used to observe the process of refraction, reflection, and diffraction for the water waves, as per the syllabus of O-level physics. Now, so what we need is state the additional apparatus needed to demonstrate refraction. All right, so refraction for the water waves happens due to change in depth. It has to be kept in your mind. The refraction in the water waves is caused by the change in depth of the water. The refraction in light is caused by the change in medium. For example, light travels from glass to air, refraction occurs. But in the water waves, the refraction occurs due to change in depth of the water. So what you need is, you can have a rectangular block, a wooden block, or a glass block. Generally for our experiments in our science lab, we do have a glass block. We just place it somewhere over here. All right, so you place this kind of glass block somewhere in the ripple tank. The place or the premises on which you place this glass block, the depth of the water would be decreased, because some of the portion in the ripple tank is already being occupied by that block. But this question was just about for the additional apparatus, so it has to be glass block, or you can also say wooden block or anything like that. Draw on figure 8.3 to show the refraction of the water wave. Label a boundary where refraction occurs. Okay, so we have to place, and this question of 3 marks. Okay, very good question we have here. 3 marks. So we have to show the process of refraction. We have to draw the wavefronts of the normal waves. Then we need to place a barrier beyond which the refraction occurs, and then we also need to show the wavefronts of the refracted waves. All right, so let's start with the normal wave. Yeah, first I can draw a barrier. So let's say the barrier is here. This is a barrier. The barrier is placed, or the glass block is placed at an angle. Even if you don't place it at an angle, the refraction would still be there, but in that case, the change in direction would not occur. Because if you place the barrier perpendicular to the direction of waves, then there would be no change in the direction of the propagation of wave. But if the wavefront, if the barrier is placed at an angle with respect to the incident waves, then there is some change in the direction of the wave as well. So let's say the waves, the water waves were coming from the left side towards the right side. All right, then you can represent the water waves with the help of wavefronts. So I'm going to draw the wavefronts here, and from the wavefronts they'll also be extracting the information about what you call that, the wavelength. So make sure the spacing, you need to be careful. So this one is the reference. Then another one here. And the distance between these waves has to be constant, because the distance between two consecutive wavefronts, it represents the wavelength. All right, and one, I can add a couple of waves here. All right, so that should be enough. Now let me just streamline these waves. So that these waves look okay. Yeah, the other one, these are the images. Yeah, but so the main thing that we're trying to observe here is that the distance, or the separation between these waves, represents the wavelength. So this is the standard wavelength, whatever the wavelength is, 3 centimeter, 4 centimeter, we drew it to our choice. But after the refraction, let's say this side, the left side, was deep water, because behind it there's no barrier. And this is your barrier, which is placed at an angle with respect to the horizontal, or with respect to the um, direction of propagation of waves. And the right side is shallow water. Shallow water because once you place the barrier in it, some of the volume of the water is being occupied by the barrier. So this side would be shallow water. And yeah, I can draw one more here. That'd be, I can just copy and paste this one over here. Yeah. Yeah, this one is fine. Now we have to refract the waves. We have to show the refraction. Now possible ways are the wave might be bent on this side like this. The waves might be bending on this side, or the waves might be bending on the other side. So there are two possible ways that we can bend the waves. Firstly, we can bend them inwards, and the other possible option is we have to bend the waves outward. Now, which one of these two choices do you think would be valid? One is bending the waves forward, like this one. And we draw another one. We bend the waves forward. We bend this one as well forward, and after bending, it will look something like this. So let's say we have bent the waves forward. Now, there would be a problem in that case. We understand that the distance between the wavefronts represent two consecutive wavefront represents the wavelength. So the wavelength was that much, might be 3 centimeter or whatever in on the left side. In the deep water, it was 3 centimeter, let's assume. But as the waves enter the shallow water, the wavelength should be reduced. That's a fact that the water waves have more wavelength in the deep water. But here it appears that the wavelength, instead of being decreased, has actually been increased because this spacing is much more than this spacing. So we have to bend the waves in such a way that the spacing should actually be decreased, and the only possible way is to bend the waves backward. And matter of fact, waves do get bent backward because the waves are lagging. As they enter the shallow water, their speed decreases and the waves appear to lag. So the lagging waves, they would be bending backward. So here's the first one getting bent. Then we draw the second one here. I need to be careful with the directions and everything. Once when we're doing on the sheet of paper, is quite easy to do it over there. And also bend the third one, but the spacing among any two consecutive waves, even on the right side in the shallow water, should be same all across the shallow water. All right, now these are your wavefronts that have been refracted, and this time if you notice that the distance between two consecutive wavefronts is now smaller. It is in the shallow water, it is smaller as compared to the wavelength in the deep water, and that is consistent with our understanding of refraction of the water waves. Figure 8.4 shows a connection to the internet made from a remote station A using a satellite above the Earth's surface. Data is sent between the station A, this is station A, and station B. We're not sending the data directly from station A and station B because there might be lot of obstacles and You need to consider a lot of things, right? It's not easy to send data directly between the two stations because of those hindrances. Rather, we are sending the data to the satellite. So station A sends the data to satellite, and then satellite transmits the data to the station B. Station B is connected directly to the internet using optical fiber. Okay, the speed of the microwaves is 3.0 into 10 to the power 8 second. Matter of fact, this is the thing that you need to memorize as well. This is speed not only for microwaves but for all the waves in the electromagnetic spectrum, including light waves, X-rays, gamma rays, radio waves, infrared, ultraviolet. All of these waves have the speed 3 into 10 to the power 8 meter per second. Station A and Station B each 560 kilometers from the satellite. Calculate the time taken for the data to travel from A to B using microwaves. So what you can do is you can, first of all, you can double the distance, because first the data, if you have the data here, okay, this is the data in, let's say, binary form. So your data first has if it needs to travel to the satellite covering a distance of 560 kilometers, and then it has to, from the satellite, in order to reach the station B, it has to further cover a distance of 560 kilometers. Now we write down the formula that relates speed, distance, and time. And that formula is speed equals distance over time. All right, this is the formula for speed. We can rearrange it for finding the value of time, and time would be distance over speed. Distance can't be in denominator. So the total distance was 2 times of 560 kilometers, but then you need to convert kilometers into meters. So I'll be multiplying 560 by 1000, so that would give 3 zeros followed by 560 divided by the value of speed, which is 3.0 into 10 with power 8. So we hit it on the calculator, and let me know what do we get there. After you hit it on the calculator, this is the answer you get in two significant figures. All right, so the all the zeros till the first non-zero digit on the left side, all those zeros are non-significant, whether they are after the decimal or all the zeros till the first non-zero digit are non-significant. The same data can be sent from A to B in a shorter time along the surface of the Earth using infrared waves to carry the information in the optical fiber. Say one property that the infrared and microwaves have in common. Like I said, infrared and microwaves, both of them belong to a family of waves from the electromagnetic spectrum, and hence they have same speed. So same speed. Both have the speed that is 3 into 10 to the power 8 meter per second. All right. What do we have after that? Suggest one other advantage of using optical fibers to connect station A and B directly. So what they're saying is, instead of using the satellite, what is the advantage of connecting the station A and station B directly? Now, if they're connected using optical fiber or any cable, no, we have to use optical fiber. Using the optical fiber, if they are connected using the optical fiber, then there's an advantage in a sense, because the transmission of the satellite depends on a lot of things. It depends on the availability of the signal. It depends on the atmospheric conditions. It depends on the weather. If the weather is not fine, there might be disruption or disturbance or the noise or the static in the signal, in the transmission. So it depends on the environmental conditions, especially in the it depends on weather. On the other hand, the communication using the optical fiber does not depend on these external factors. It does depend on the optical fiber itself. If there's a crack on it, if there's some breaking in the optical fiber, yeah, then it may disturb the signal, but this is very less likely to happen. Let us start with this one. The past paper questions, paper 1 of general wave properties. Here we have the first one numbered as 5. A water wave moves quickly in deep water. All right, that's a fact. The water waves have more speed in the deep water. The wave now enters the shallow water as its speed decreases. All right, so speed in the deep water is greater than the speed in the shallow water. That's a fact. And this is something that we study independently. Which row shows what happens to the frequency of the wave and what happens to the wavelength of the wave as the wave enters the shallow water. So for this one, we know one thing, that the frequency of the wave, now it changes. Frequency does not change in this case. Whether the water wave move from deep water to shallow, shallow to deep water, the frequency remains same. So that discards option A and option B from here, because that one read frequency decreases. So frequency has to remain same. Now what about the wavelength? Since speed decreases in shallow water, so does the wavelength. So wavelength also decreases. So it has to be the answer C. So this is what happens in the shallow water. The wavelength decreases as speed decreases. That's a fact. They ask it many times in your O-level physics exam. Moving on to the next one. Kind of an extensive diagram. The diagram represents circular wavefronts coming from point S. The wavefront strikes a barrier and are reflected so that they appear to come from S. All right. So they strike the barrier and then they are reflected. Which diagram shows the reflected wave fronts? This is what we need to find out. Which diagram shows the reflected wave front? So this is the option A, option B, option C, and option D. Now, the most important thing, like they say, like they have said, the wave fronts strike the barrier and they are reflected so that they appear to be coming from point S1. And that was the standard case. You have to take this one for the reference. Now, for the option A, we have to discard option A and option B because the waves appear to come from S1. So they should be bent away from S1. So the bending has to be opposite and they should be on the same side of the barrier. If the wavefronts were on the left side of the barrier, they should still be on the left side of the barrier because in the process of reflection, the waves bounce back in the same medium. They don't cross over, they don't penetrate through the barrier. So A and B out of the window. All right, and then we have C and D. Now in reflection, the wave, all right, the shape of the wave does not change. All right, whatever wave is striking the surface, the same wave would be coming back. So you see your wave is not too circular. It's kind of pretty much straight line, a little bit curved. So that one is consistent with the option D. In option D, you have the wavefronts which look pretty much the same as of the incident wavefronts. And these one your incident wavefronts. We had to choose between C and D because C and D both show the waves being reflected in the same medium, but we discarded C because C shows the wavefronts changing their shape, which does not happen in reflection. All right, moving on to the next one. Here we have number dash question number 5. Sorry, which one is that? Question number 7. So in this one, the diagram shows the waves, a water wave approaching a barrier with a gap. The wave reaches a point P. What is the name of the effect that causes the wave to reach the point P? This is called diffraction. That's a fact. If there is a barrier and the gap between the barrier is pretty much the size of the wavelength, right? So if the separation of the barrier is D and D is approximately equal to the wavelength or even slightly smaller than the wavelength, then we see that there is a process of diffraction that takes place. So these waves would be bent around the corners and they would look something like this, and that would make the waves pass through the barrier. So this process is called diffraction. That's fact-based, information-based. All right, so moving on to the next one. Here we have title as number dash 8, which row correctly defines a type of the wave and gives a correct example. So longitudinal, parallel, radio waves, light waves, these are transverse wave. A and B calls them longitudinal wave. So we can discard option A and B. We're left with option C and D. According to the definition of transverse wave, these waves, the particles in those waves vibrate perpendicular to the direction of energy transfer or to the direction of wave travel. So this one has to be option D. So D is the right answer for this one. All right, then we have question number 9. The diagram represents a water wave, and then we can see the water wave over here. Which row shows the amplitude of the wave and the wavelength of the wave? So amplitude and wavelength. Now, in order to find the amplitude, make sure you're finding the amplitude from the mean position. So the maximum distance of the wave from the mean position. All right. So this is a point where many of the students are trapped. They commit an error over here. They just notice, okay, the maximum distance is 2, the amplitude would be 2. No, it's not. That's not the case. In order to find the amplitude, first you need to draw mean position. All right, you need to draw the reference line that splits the wave into two equal parts. The upper part would be called crust and the lower part would be called trough. So the distance, maximum distance from the central line to the top would then be 1 meter. So that your amplitude would be 1 meter. So C and D discarded because their amplitude is mentioned wrong. Then you're left with the wavelength. Wavelength is the distance between two consecutive crusts. Wavelength can be defined in different ways. The length of a complete wave, or the length between two consecutive crusts, or the length between two consecutive troughs, or the length or the distance between two consecutive in-phase points. Whatever way you want to choose. This one would be convenient. Over here would be convenient to define wavelength in terms of the distance between two consecutive crusts, because they have mentioned the distance from crust to crust. But in 4 meters, we have moved to crust. All right, we bypass this one. So the distance between two consecutive ones would be 2 meters, and then 2 meters from there to the next one. Only then we can have 4 meters from this point to this point. So the distance for two consecutive crusts would be 2 meters. So it has to be option A. A is the right answer for this one. Moving on to the next one we have here. Yeah, so here we have the next one, number dash 10. And this one is uh, the diagram shows a side view of the water wave at a particular time. The diagram is drawn full scale. What statement about the water wave is correct? About the wave is correct. It is a water wave. So first of all, we know it from the fact that water waves are transverse wave, right? So option A and B, they call water waves longitudinal. That's a mistake. We discard option A and B from here. Right? These are transverse wave. How do we know that? When we completed the theoretical portion over there, we explained why water waves are transverse wave. And the second thing is, this diagram shows their uh, waves with respect to time. Like, how do the waves move with respect to time? So the x-axis here is representing time in seconds or milliseconds, whatever it is. So from, if time is given on x-axis or one of the axes, then we are able to comment on frequency or time period. So it would be option C. Because wavelength, we cannot comment about the wavelength unless we are given with the view of the waves with respect to the distance covered. But in this case, the distance covered is not given, rather we are given with particular time, so it has to be frequency. Moving on to the next one, that is number dash 14. So for this one we have, which row states two properties of sound waves. So first of all, sound waves are can travel through, not through vacuum. Right? Sound waves cannot travel through vacuum. A and B, we can discard them. Sound waves are longitudinal waves because they travel in the form of compression and rarefaction. Right? So this region for the sound waves might be compression, followed by a region of low pressure, which we call rarefaction, followed by a region of high pressure, now we call compression. So compression followed by rarefaction followed by compression, and that is how the longitudinal wave propagates. So C is the right answer. Water waves, sound waves can travel through medium, and medium can be anything: solid, liquid, gas, and type of wave is longitudinal. All right, then we have the next one. The diagram represents water waves in a tank. Which diagram represents a wave that changed speed? So the wave that changed speed, we have to represent that. This is a process of a, a poor form of diffraction, but in diffraction speed doesn't change. This is a this is a case. B is a case where diffraction is prominent, or once again in diffraction speed does not change. C is indicating the process of reflection, the waves getting reflected by the barrier, but once again in reflection the speed doesn't change. D represents the process of refraction, and in refraction speed does change. If the waves enter from deep water to shallow water, the speed decreases. Moving on to the next one, titled as question number 16. What is the frequency of the wave? So frequency is not anything, it does not have to do anything about the distance, so we can discard distance. So the number of wave fronts produced per second, yeah, this one it is the number of waves per second, the number of wave fronts, or the number of thrusts produced per second, or the number of troughs produced per second. That would be the wave fronts. Sorry, that would be the frequency. Measured in hertz. Hertz can also be written as per second, or we can also call it cycles per second. Generally frequency of moving objects, it is measured in cycles per second or revolution per minute, rpm, but for the waves we just call it hertz. All right, then we have the next one titled as question number 19. In an experiment to measure the speed of sound, the student uses stopwatch to find time taken for the sound wave to travel from X all the way to the Y, to the point Y. The table shows the results, and then you can see the results as well for the time in the first attempt, second attempt, third, fourth, and in total 6 attempts. Which value of time should be used to calculate the speed of sound? Out of these 6 values of time, which value should be used to calculate the speed of sound? This is a question that we have. All right, so we don't use any of these values, rather we find out the average value. So we have this one plus this one plus this one plus this one plus this one, and whatever the answer is, we divide it by 6. And let me know what do we get from here after adding all of them and divided by 6. Should be 0.6. All right, so that should be it. I mean, once you add all of them and you divide it by 6, this is what you should be getting. All right, anyway, moving on to the next one. All right, so here we have numbered as question 22. Which waves are longitudinal? The light waves are transverse waves. They are from the electromagnetic spectrum. Microwaves from electromagnetic spectrum. Water waves are transverse waves. The water waves would cause an object sitting on the water or placed on water move up and down, thereby indicating that the particles in the water move up and down and the wave propagates sideways, so that would be transverse. Sound waves, however, produced by trumpet or anything, even by our vocal cords, sound waves are longitudinal. Then we have the next one, question number 23. Waterways travel more quickly on the surface of the water when the water is deep. A stone is dropped from at a point X into a pool of varying depth. The diagram shows the first wavefront on the surface of the pool. The region between X and which labeled point is likely to be the deepest. So the deepest point would be the point that has that is at the maximum depth, and that is C 23. How do we know? I mean, we have studied one thing uh, for the waterways, that the deeper the water, the more would be the wavelength of the waves. So point C represents the highest wavelength, and hence point C has to be the deepest. Yeah, I mean, I don't know how did my setting got messed up. All right, let's complete a couple of more questions. Uh, then we have the next one. A lighted candle is placed in front of a loudspeaker that is making a loud, steady note. The candle flame vibrates because of the sound wave. Which type of wave or sound waves, in which direction does the flame vibrate? So, this is what we have. First of all, sound waves are longitudinal waves. So transferred, crossed out. And if the sound waves are propagating in this direction, it would make the particles vibrate parallel to the direction of sound wave. Otherwise, it won't be a longitudinal wave. So, since from the loudspeaker, the waves would be emitted from the left side to the right side or in a horizontal direction, so the particles of the flame would also be moving left to right. So it would be option C. I mean, and I mean, that's a very uh, pretty much common sense question. If you try to blow the candle, all right, because sound waves actually propagate by the movement of the air particles. In air, it moves by the movement, by the vibration of the air particles. So if you vibrate the air by some other way, for example, by blowing, if you try to blow the candle, so the air would be moving to the right side, and the candle, the flame, would be shifted to the right side. So the motion of the candle flame would always be left to right. So C is the right answer for that one. All right, then we have this, the next one, number dash question 26. A small boat in a harbor is protected from the waves on the sea by harbor walls. And then you can see that some waves can curve round the harbor walls and reach the boat. What is the name of this effect? Fact based, uh, knowledge based. Whenever the bending or rounding of waves is discussed, I mean, how do the water waves move from here around the harbor walls? It moves by the process of diffraction. So that one was fact based. Then we have the next one, titled as question 28. A police car sounded siren when traveling to an emergency. The siren produces two different sounds, P and Q, which are emitted alternated alternately. The diagram represents the sound waves emitted by the siren. Which of the two sound P and Q is the louder, and which one has the higher pitch? So the louder would be the one with the more amplitude, whose amplitude is more, and the sound with more pitch would be means would correspond to the sound which has more frequency. So if you compare P and Q, which one has more amplitude? P. So the sound P would be larger. That means C and D out the window. And then which has more frequency? It is Q, because for the Q, the waves are compressed, the waves are close to each other. So B would be the right answer for this one. All right, so let's move on to the next one. Here we have question number 32. Water waves may be used to demonstrate refraction by making them pass into water of different depth. What is the water wave chain? Why does the water wave change direction as they pass into the shallow water? Speed of the wave, frequency of the wave decrease. First of all, frequency of the wave does not change whether the wave enter from deep water to shallow water. Matter of fact, the speed of the wave would be decreased as the waves enter the shallow water. So it has to be option C. Speed and wavelength. These are the two things that decrease as the wave enter to the shallow water. All right, moving on to the next one, question number 33. Yeah, question number 30. A boy throws a small stone into a pond. Waves spread out from where the stone hits the water and travel to the side of the pond. The boy notices that 8 waves reach the side of the pond in a time of 5 seconds. What is the frequency of the waves? So in 5 seconds, So in 5 seconds, we have 8 waves. We need to find frequency. Frequency stands for the number of waves in 1 second. So in 5 seconds, there are 8 waves. How many waves would be in 1 second? It's just a question of cross multiplication. I mean, you don't even need to do that. You can simply divide it, hit it on the calculator. But if you're not really good with it, just cross multiply that. So it would be x equals to, or the frequency equals to 8 over 5. And answer can't be anything less than 0, less than 1. A and B can't be the option. Answer can't be 40. I mean, it can't be that big. You're dividing two numbers which are pretty much close. So 40 can't be the option. C can be the only reasonable option that you can have. So you can do it even without the calculator, because the other options are dramatically different. You can straight away ignore them. Here we have the next one then. On the left side, we have to represent transverse wave. On the right side, we have to represent longitudinal wave. So radio wave and sound wave. Radio wave is part of the waves from the electromagnetic spectrum. All the waves in the electromagnetic spectrum are transverse wave. And longitudinal waves, in the syllabus for physics O levels, the only longitudinal waves that you need to really study are sound waves and the waves produced in a spring or a string or a rope. but those are for the special cases because you have to move the spring or the rope in a certain way to produce longitudinal wave. The most important one, longitudinal wave, in the entire syllabus for O-level physics is the sound wave. If you remember this one, that sound wave is a longitudinal wave, then you can uh, cross out the incorrect options and you can get away with that. All right, so let's do this one as well. A tuning fork is marked with the number 320. This indicates, okay, so this one, yeah. So this indicates the size of the frequency. What does this mean? So the length of the tuning fork is 320 millimeter. Frequency has nothing to do with the length. The note from the tuning fork will last up to 320 seconds. Not really. The sound waves produced by the tuning fork travel at 320 meter per second. Nope. The tuning fork vibrate 320 times every second. That's it. D gets the last laugh. 320 vibrations per second, and this is how we define frequency as number of vibrations per second. This one looks interesting. The question of graphs are always interesting, and here we have question number 38. The diagram represents two sound waves. The scale into diagrams are same. Means if this one is, if one block represent 1 second on the left side, then one block will represent 1 second on the right side. This is what they mean by the scale. And also for the y-axis, if one block vertical represent 1 millimeter, then on the right side it would also represent 1 millimeter. Which statement describes the waves? Now if we just take a look at the waves, they have the same maximum distance, means they have same amplitude. And if they have same amplitude, they will be having same loudness. So both these options, A and B, you can throw them in the recycle bin, because A and B, they say the two waves have different loudness. If the amplitude is same, they would be having same loudness. What's the difference? The difference is in the frequency. This one has low frequency and this one has high frequency. All right, because if let's say time till here represent 1 second, then over here it would also represent 1 second. So this one has frequency of, let's assume 1 hertz, because only one wave in 1 second, but the second one would have two waves in 1 second, so its frequency would be double than the one on the right side. So the more the frequency, the more the pitch of the sound. So these two waves have same loudness but different pitch. Frequency of the sound waves determine pitch of the sound wave. The higher the frequency, the shriller the sound would be. Kind of the sound of the girls or the babies, the kids, they have high pitched sound. High pitched sound corresponds to high frequency. Low pitch sound corresponds to low frequency. Low pitch sound has higher wavelength, but it is kind of grave, kind of bold sound, and that sound would be having low frequency. Hence, we call that sound low pitched. Alright, so we starting off with this one question, number 39. The diagram represents a wave. How many wavelengths are there between x and y? So we are represented by 2 points. We are provided by 2 points, point x and point Y. And then the question is how many wavelengths are there between point X and the point Y? So, point X is a line passing through the crust, and till this point, till the next consecutive crust, we get one wavelength. But if we stop till the trough, we'll get half the wavelength. So this one would be complete wavelength, and after that, we're not going for the full wave. We're not going for the next crust. Rather, we stopped at the trough. So from there, we get half the wave. That is lambda over 2. So lambda from the first, lambda by 2 from the second, the total would be lambda and a half, or 1.5. So whatever the wavelength is between X and Y, it would be 1.5 of that value, 1.5 of the wavelength. Alright, on to the next one. The diagram shows the surface of the water in a ripple tank. A wave is traveling in the direction of the arrow towards the gap in a barrier. What happens to the wave as it passes through the gap, and what happens to the shape of the wave fronts after passing through the gap? Now, first of all, the wave can only pass through this barrier by a process that we know by diffraction. So C and D can be thrown out, can be discarded straight away. And in order for the wavefront to pass through the gap, they must be curved. And in diffraction, we study independently that the waves curve. So A has to be the right answer for this one. Here we have the next one. Sound waves may cause an echo. What happens to the sound waves to cause an echo, and what is the nature of the sound wave? So we can deal with this one first. What is the nature of the sound waves? Sound waves are longitudinal. They propagate by compression and rarefaction. These are not transfers, so we can discard these options B and D. And the process of echo is produced due to multiple sound waves being heard. So that is by the process of refraction. So here we have the next one. A girl notices that when she shouts into a cave, she hears an echo. Which wave property causes an echo? Once again, the repetition of the same concept. So this has to be reflection. Then we have the next one. In a test, a car horn is found to be too loud and the pitch of the note is too high. What information does it give about the amplitude and the frequency of the sound wave? So too loud means amplitude is high, lot of amplitude is too large, and the pitch of the sound is too high. Pitch of the sound is too high means frequency is also too large. So both amplitude and frequency are too large. All right, so A would be the answer for that one.